The first thing we're going to do with this Yaskawa servo motor is do a current test, and we hit current test right here, and you can see we've put up a waveform that this is just commanded torque. We've done some ramps, we've done some steps, we've done some sine waves. The red actual current is following reasonably well. You can see that there's some delay. That's just the nature of EtherCAT. But all in all, we know that this is working. So we're going to go in here and do a step. All of our parameters are set for 0, so I'm going to double KP, which puts in 1%. And I'm just going to keep doubling KP until its response is a little too big. Now we're going to put in KD until we can show that we're under control and it's actually increasing the stability. Once it's below this step line, we're going to go and double it again. We're going to go back to KP. Now we're going to go and do KD. Now all you need to do when you look at this is see that if it's too low, you add KP. If it's too high, you add KD, and you start to walk this in towards better performance. Even right here, you can see that in 21 milliseconds, we've got a servo done. I mean, it's finishing the step move. It's reasonable. Now that's a little slow, but still, we're in the ballpark. Now I'm just going to go up by 1.1, so I'm just adding 10% here. Now I'll do KD the same way, and I'll just click it a couple times, and we'll bring that back down, add some more KP. Again, KP is response, KD is stability. And you can just work this in and continue back and forth. It's an iterative process, but you do know exactly which way to go. Right now we're down to 14 milliseconds. I can add a little bit more on this. I'm down to 13.5. This is a good running servo at this point. Let's do a trapezoidal move. So we go in here to T-curve and we hit this. Now you can see the blue is the commanded velocity and the black is the actual velocity. The purple line here, this is the actual torque required. This is the torque that we calculated and sent to the drive. This red line is the instantaneous error. So if you look over here above the red, right there, when I hold my cursor there, it says 1.8 degrees. So we're off by 1.8 degrees while we're doing this acceleration at 90,000 degrees per second. So let's go in, and even here during top speed motion, we have a small error. It's mainly because this motor has a seal in it as well as a bearing, but the seal itself adds a little bit of friction. So we're going to go in and click KV, and we're going to try to work this down by saying, give me a little assistance just because I'm moving at 3,000 RPM. Now I'll go up by 1.1, so this is a 10% increase. Right there, that looks as good as it's going to get. So I'm going to go to KA, which is the acceleration feed forward during acceleration. So I'm going to just double this and continue to double this until you see that this red line on the left starts to walk its way down, which it's now doing. I overshot that a little bit. I'll go back, and now I'll just go up by 10%, and I can just keep clicking this and doing them a little more. Now I'll do 1%. So here we are. This side is pretty good. Notice it had no effect on the deceleration side. That's a separate parameter. The reason we choose to do that is simply that on the way up, on acceleration, friction hurts you, and during deceleration, friction helps you. So again, we're going to do these separately, and up it comes. Now once this starts to move, it goes pretty quick, so I'll just go up by 10%. I can just do a couple of these. We're in the ballpark right there. Now at this point, you can see this is quite a spike that we need, and if you could hear this motor, there's a little bit of vibration there. You can hear these serious peaks. So and the total error right now is 0.9 degrees. Now most of the trip, you're down in the noise, but right here the error is minus 0.9 degrees. So we'd like to do a little better, so we're going to do an S-curve. Instead of having these sharp edges, we're going to do an S-curve, and here you'll see that we've rounded off these corners. Our error has gotten significantly better. We're down to 1/4 of 1 degree, and now we see, because the scale has changed, now we see we could use a tad bit more. I'll just go up a few 1%ers on this KA. You can tweak these any way you want. Now you can also see that off to the side, we've got a little bit of steady state error at the end. We're going to use KI to try and get rid of that. At this point, the derivative term is no good because we're not moving. None of the KVs or KAs are working because, again, we're not moving. So KP is simply not enough to overcome the friction in that seal. So we're going to use the integral where we're going to let that error build tick after tick until finally it becomes enough to cause motion, and you can see it working its way down even as we speak. So right now what you've got is a fully tuned servo with about 1/4 of a degree using these parameters. So that's as quick as we think you can tune a servo motor. Thank you very much.